Okay, so we're at Fermi National Accelerator Laboratory. This is in Batavia, Illinois. This is about 1 hour from here. And today we're going to be talking about how this accelerator complex works and what it does for neutrino physics. So the story starts, first I have to do a brief advertisement, which is that Fermilab is now open to the public. So in particular, you can visit the Bison Herd, you can visit the Letterman Science Center, and for more information, you should go to fnal.gov to see how you can visit and what you can see. Okay, so the first thing I want to talk about is this ring here. This ring is called the main injector. It's one of the 2 particle accelerators at Fermilab. It actually accelerates protons that go into the larger ring, but for the purposes of this story, we're just going to be talking about the protons that go through the main injector. So these protons are accelerated up to energies of 120 giga-electron volts. And then there's a magnet placed right at the interface where this arrow is pointing that can divert that beam into a block of material. And when that happens, those protons smash into that material and produce a big spray of pions. And those pions decay into muons and muon neutrinos. The muons are stopped by the Earth. They don't travel that far, but the neutrinos keep going. And they really keep going. So that neutrino beam at Fermilab travels through the Earth about a distance of 500 miles. And so on this figure here, this yellow line is showing you the curvature of the Earth. The neutrinos go straight through, though. So actually, in total, the beam passes about 6 miles underground at the deepest point. So 500 miles, and the beam is aimed at Ash River, Minnesota. And you can see the kind of the journey it takes. It actually goes a little bit through Lake Superior, which is kind of a fun fact. Just the kind of deepest point of the lake there, the tip. But anyway, in Ash River, what's there is a giant detector. It's called NOVA. This is a picture of the NOVA far detector. And just for a sense of scale, I intentionally made it a little hard to see, but there's actually a person there, standing there. So this is a really big detector. And what happens when the neutrino enters the detector, this is just a cartoon of what happens. The neutrino enters, and then we get a big spray of particles. And that spray of particles is also big. So this what you're seeing here is the result of a neutrino interaction that's about 14 meters long. So what you're seeing is not the neutrino itself, but the particles that are produced in this interaction. And we measure these to tell us something about properties of the neutrino. We can also reconstruct these, so identifying the particles from how they look. This long one, we think it's a muon, and then these red ones, we call them hadrons. They're just combinations of other charged particles. Okay, so that's where we're going. We're going to look at how that fits into our big picture of neutrino oscillations. So this lecture is entitled Reactors and Neutrino Beams, very closely related. Okay, so just brief recap the story so far. So in the first lecture, I told you about how beta decay, the beta decay spectrum having this continuous energy distribution was what motivated Pauli to send his letter to this conference to say, I think that there's an extra particle. And then Fermi came along and added a theory to that. Then took them about 25 years to actually discover the neutrino. That was done by Reines and Cohen. Then there was a team by Letterman et al. Who discovered the second type of neutrino. Last time we heard about the Homestake experiment, which started around 1967, that identified the first sign that there was something more to neutrinos than we had initially thought. So the solar neutrino problem, where there were missing solar neutrinos, and then the atmospheric neutrino anomaly, where there were missing atmospheric neutrinos. These questions were open until the Super K and SNO detectors were built around the early 90s. The results from those experiments showed very precisely what the explanation was and how those neutrinos were missing and could be found again. So what we've learned so far is that when neutrinos interact, they produce the charged lepton of the corresponding flavor. So when I talk about an electron neutrino, and that electron neutrino interacts, it produces an electron. And then there are different families of these leptons, so there's not just the electron, but there's also the muon particle and the tau particle. And they have the same properties, but they're differentiated by their masses. So the muon is a little bit heavier than the electron, and the tau is a lot heavier than both the electron and the muon. But then the other thing that we learned from the previous lectures was that neutrinos don't have one fixed flavor. So the flavor changes over time. This was a diagram I showed in the previous lecture. So on the left, you have the single neutrino picture, so 100% electron neutrino. And on the other side, you can also think of a neutrino as a combination of flavors, so a mixture of flavors. And what we want to do in this lecture today is understand how this comes about, how you go from a full neutrino of one flavor to get some kind of mixture of neutrinos at the other end. And then I'll talk about how we can measure this very precisely. Okay, so I'm going to start off with a thought experiment. So in particle physics, these are called Gedanken experiments. They were originally proposed by a German physicist. So just imagine for a second that you're in your living room reading your favorite physics textbook, and your cat is somewhere off in the other room, sleeping very peacefully. So you have this mental model in your head that your cat is in the other room, very peacefully sleeping, and nothing should be happening. But then all of a sudden you hear a crash. Oh no, what happened? So as you get up, you put your book down reluctantly, you get up to go check on your cat, and lots of thoughts are going through your head. It could be that your cat is still sleeping, but also like you can imagine all the kinds of mischief your cat has gotten up to. So you reluctantly get up to check. So what Schrödinger told us is that your cat is not just one or the other. It's not just guilty. It's not not guilty. Your cat is actually could be thought of as a superposition of these two things at once. So before you actually check on the cat, you can think of the cat as some combination of both sleeping peacefully, not guilty, not up to any trouble, and also causing a lot of trouble. The subtleties of why it's useful to think of it this way really only apply to particle physics, but to just have this mental model that one thing can have two different states until you observe it is going to play a crucial role in understanding how neutrino changes flavors. Okay, so when you observe it, you can see for sure that your cat actually was causing a big stir. Okay, so Schrödinger neutrinos. So as I talked about before, the neutrino doesn't have a definite flavor. So when the neutrino is created, the flavor is definite, but then something happens between when the neutrino is produced and when it's detected that causes its flavor to change. So in transit, we can't really assign a particular flavor to a neutrino. And to demonstrate this, I have a quick little demo, which is this very special ball. Hopefully everybody can see it. So this ball is red at the moment, and when I throw it up in the air, it's still red. So if I throw it up again, still red. Blue. Okay, so this ball has this special property that as you throw it, there's some chance that it flips from blue to red. And this is kind of a good model of neutrinos. So they start out in one flavor. So on this slide I have the new E is blue. So I'll flip this around to new E. And then in transit, I can't really tell what it looks like. But then when I catch it, I detect it, it flips from blue to red. So it can become this muon neutrino from the electron neutrino. So here's a picture just in case you couldn't see the demo. Starting out as blue, in transit it's some crazy combination of the two, but I don't know exactly what it is. And then when I catch it, I detect it. This is like seeing it in your detector. It's either one flavor or the other flavor. You don't see this in-between state anymore. Okay, so how does this apply to neutrinos? To do that, we have to understand a little bit about waves. So waves and interference. This is just a picture of two sine waves, and those sine waves are oscillating at different frequencies. They're going back and forth. You can think about these waves as clocks that are ticking at different frequencies. So in particular, the hands on the clock, when they line up, means the waves are in phase, and when they don't line up, the waves are out of phase. And so this sine wave is basically the same picture as the clocks. The clocks are just showing the kind of one-dimensional view instead of spreading it out over time. But having this clock model is going to be important for understanding neutrinos. So in particular, Mr. Louis de Broglie described in around 1924 that wavelength is not just a concept for light and waves, but it also applies to matter. So Mr. de Broglie gave us this formula for wavelength that relates the particle's mass to that wavelength, specifically the particle's momentum. So the relationship is given by Planck's constant in the numerator, and then the momentum in the denominator. That momentum can be rewritten as just the mass times the velocity. So now we have a relationship between particle mass, particle momentum, and the particle's wavelength. And then this effect was actually demonstrated just a few years later. So this is a picture of an interference pattern caused by electrons that are scattered from a crystal. And they interfere just like light waves would. So you can make the same image with X-rays or whatever your favorite radiation is, and you would see the same pattern. So it applies not to just light, but also to particles. Okay, so then back to neutrinos. So to put this all together, we're going to pretend that our neutrinos inside of them have some ticking clocks. So assign our electron neutrino and our muon neutrino a particular combination of clocks. And what's important here is just that the offsets between clock 1 and clock 2 are different, so that there's a unique combination between clock 1 and clock 2 that defines what an electron neutrino is and defines what a muon neutrino is. So with this picture in mind, what we're going to do is just run the clocks. We're going to see what happens as we let the clocks tick. So if we start with an electron neutrino, we take that same configuration of clocks, and then we let the clocks run. So what happens as the clocks run is that they get out of phase. They're no longer a particular combination of electron neutrino or muon neutrino. There's something in between. But they're pretty close to what the electron neutrino was. So we're going to call that mostly electron neutrino and a little bit of muon neutrino. In other words, the hands of the clock are pretty close to what they started at a short time after you start to let them run. But then after a while, you let the clocks run and run and run, and eventually the hands line up to form a muon neutrino. So that happens sometime later. And then you can imagine letting the clocks run even further, keep going, and eventually the hands of the clock get back to the electron neutrino. So this is the kind of way we're going to put together how neutrino flavor changes over time. And to just spell it out, so each clock in the neutrino represents a particular particle with one mass. So either mass 1 or mass 2. So I've written the neutrino here as this superposition of two particles, one with mass 1, which I'm going to call nu1, and one with mass 2, which I call nu2. So that's the first thing. The second thing is that de Broglie tells us that if the particles have different masses, then they have different wavelengths. So that's going to create these offsets. That's going to cause the clocks to rotate at different speeds. The next thing is that, as we saw, when you have interference between the two clocks, the neutrino flavor changes over time because the clocks are not quite lined up with a particular state. There's some interference pattern that causes them to be in a combination of different flavors. Now, eventually they will line up to be in that state, but you have to wait for the neutrino to get to a specific value, let's say. And everything in between is mostly what you observe. So everything in between is going to have some probability of being electron neutrino and some probability of being a muon neutrino, let's say. So then finally, we get to the crux of the matter, which is that if we observe this flavor change over time, then what we're saying is that these clocks have different frequencies. And from de Broglie, we learn that the different frequencies mean that there's a relationship between the frequency and the mass of the particle. So if they have different frequencies, then they have different masses. And you can't make both of the masses 0 and have them be different. At least one mass has to be positive. And so this is why we say that neutrinos have mass and that the mass causes them to oscillate. So we call this whole picture of neutrino oscillation, of neutrino flavor change over time, we call it neutrino oscillations. And this was the subject of the 2015 Nobel Prize that I mentioned last time, which went to the Super K and the SNO collaborators who showed this process was happening using atmospheric neutrinos and solar neutrinos. So you can see here in the line that the prize was awarded for the discovery of neutrino oscillations, which shows that neutrinos have mass. And this was the logic. This is the logic behind it. Because we have neutrino flavor change over time, the neutrinos have to have mass. At least one of these states that the neutrino is in a superposition of has to have non-zero mass, is the argument. Okay, so that's neutrino oscillations kind of in a nutshell. But let's look at what this implies for an experiment. So quantum mechanics predicts that the pattern, or the particular pattern of observing each flavor. So what I've drawn here is the probability on the vertical axis, and then the L over E, which is the distance the neutrino travels divided by its energy on the horizontal axis. And quantum mechanics actually prescribes a very particular pattern for what this should look like. So I've just drawn an example here. This is if we lived in a world where there were only 2 neutrinos. The story gets a little bit more complicated when you add a third one, but that detail isn't so important right now. What is important is just that this probability changes as a function of the distance you travel and the neutrino energy. The only problem is that quantum mechanics does not tell us the amplitude of these oscillations. And it also doesn't tell us the frequency. So we're still stuck. We still don't really know anything about neutrino mass. We can't say what the particular values are, and we can't say what the amplitude of the oscillations is until we go and measure these things. So we know that oscillations exist. We see them in the atmosphere. We see them in the sun. And we have a mathematical model that we can use to test, but it has parameters that we have to go out and measure. Okay, so measuring oscillations really boils down to two things. There's a common experimental design where you either look for appearance or disappearance. And what I mean by that is in the case of appearance, you're looking for flavors that you didn't start with. So if you create an electron neutrino, you're looking for anything but an electron neutrino at the other end of your experiment. On the other hand, you can look for disappearance. You can say, I created an electron neutrino. I want to see how many electron neutrinos are left at the end of my experiment, and then I will conclude that the missing electron neutrinos have changed flavor or have oscillated into muon or tau flavor neutrinos, for example. And just like in the previous picture, what we're trying to measure here is the amplitude of the oscillation, so how big this effect is, how many excess events do we see in the case of an appearance search, or how few events are left in the case of a disappearance search. That tells you something about the depth of the oscillation. You can also measure particularly where the maximum effect of this oscillation happens. That will tell you the frequency. So that's a probe of the neutrino masses, because the oscillation frequency depends on the difference between the masses to get that wave interference pattern. So this is what we're going to go look for. And ideally, we would set it up so that in our experiments, we test all different combinations. We start with an electron neutrino, we see it oscillate to tau neutrino, or we start with a tau neutrino and see it oscillate to a muon neutrino. But in reality, we can't test these because there are certain configurations that we haven't figured out how to produce. So for example, we don't have a tau neutrino beam, or really an electron neutrino beam that's high enough energy to create tau particles if through oscillations. So there are some constraints on what exactly we can test, and we'll explore why it's useful to have both reactor neutrinos and beam neutrino experiments to do this. Okay, so I'm going to start off by talking about neutrino beams. I just want to clarify that this is probably not what we're going to talk about. Come back for Compton lecture 2300, maybe, let's say, and you can maybe get a speaker to talk about this one. But for today, this is not the neutrino beam in question. Okay, so going back to this picture here, neutrino beams, what a neutrino beam does is it produces a high energy muon neutrino. So just like in that sequence I showed at the beginning, the muon neutrino produced at Fermilab through their neutrino beam, that has an energy of a few GeV, so a few giga electron volts. And what we're going to look for is for that muon neutrino to transition into a tau neutrino or an electron neutrino in our experiment. So we can either look for muon neutrino disappearance, we can look for how many muon neutrinos are left, and we can also look for the appearance of either an electron neutrino or a tau neutrino. So I'm going to start off just by describing a little bit how a neutrino beam works. So we saw in the big picture, but let's zoom in a little bit. So first you have this proton source, like at Fermilab's main injector, which is accelerating protons. Those protons then go onto a graphite target. So here's a picture of the graphite target in this neutrino beam at Fermilab. It's a lot of rows of just little graphite blocks, and that allows you to swap them in and out. It's about 1 meter long, so it's not a huge thing. And the protons impinge on this little red circle that I've shown here. Next, the pions that are produced actually go through a series of magnets that are called horns. And the magnets, what they do is they bend the particles into a beam. So by default, the particles just come out as a big spray, but you need a magnet to bend them into a beam that's collimated, that's focused. So the magnet does that. So this is a picture of the horn assembly at Fermilab, and the reason it's called a horn is because inside this there are these big metal things that look like horns, that look like the musical instrument. But these are really just electromagnets. So current is flowing around these to create a high magnetic field in the middle that focuses these particles. And a great analogy is a lens. So you can think about light passing through a lens. The electromagnet is doing the same thing. It's bending these particles and focusing them. Next, the pions just travel. They're just allowed to propagate in what we call a decay volume, but it's really just a fancy word for a room or a pipe that's under vacuum. So the pions just travel through this pipe, and somewhere along the pipe, it's random, but they'll decay. Then we put some material to absorb the muons to prevent them from going further, and the neutrinos just keep propagating through, all the way to Minnesota, for example. So you're left with neutrinos. So the way these experiments work is what we call long baseline experiments. So we're going to have our neutrino beam at Fermilab, let's say. We're going to put a detector very close to that source, a near detector. And what it's going to do is tell us or confirm that we have the correct number of neutrinos that we expect. So before any oscillations have taken place, then we're going to let the neutrinos oscillate. So we're going to let them travel for a very long time. And then we're going to put another detector all the way at the end. So for example, in Minnesota, 500 miles away, where hopefully we see that the neutrinos have all oscillated, or some fraction of them have oscillated. And then we can count the ratio between the near and the far detector, and we can do this as a function of energy to figure out where the oscillation maximum is, or where the frequency of the oscillation is. So this is the big picture experimental setup. Right, and then I just want to emphasize that this is really quantum mechanics happening over distances of hundreds of kilometers. So it's really quite an exciting phenomenon to be able to see and test very precisely. Okay, so I'm going to talk about the first long baseline experiment. So this is an experiment called K2K, and it was built in Japan. K2K stands for KEK to Kamioka, so it's an acronym within an acronym. And the way this worked was that there was a particle accelerator. And so the distance between these, which for this experiment was 250 kilometers. So there was a particle accelerator at KEK lab, and it's producing about 10 to the 12 protons per second with 12 GeV of energy smashing into a target. Those pions that come out of that interaction are being focused and directed all the way across Japan to Super Kamiokande on the far side. So we heard about Super K last time. This was the experiment that was used to measure neutrino oscillations using atmospheric neutrinos in about 1998. So it's been repurposed for this experiment. It's now the far detector of this long baseline experiment. There's also a near detector, so a mini Super K placed pretty close to the beam source. And I think this is funny. So this is like a very scaled down version of Super K, but it also looks huge, right? I mean, these people are very small compared to the detector. So then Super K is 50 times this size. So it's really quite huge. And anyway, this was the experiment that was done. But first, so I'll say that this was set up in the late 90s and then started taking data after Super K's atmospheric neutrino result had come out. But unfortunately, there was a pretty major accident before this experiment could start taking data. And what happened was that after Super K's initial run, they had drained all the water, and then they were refilling the water up. And as they were doing that, the glass window on a single photomultiplier tube shattered. So this is a photomultiplier tube, smaller than the ones in Super K, but this is the glass that is on top of this. And this device is used to detect the light that measures the particle interactions. So what happened was, I have some frames shown at the top. I'm not sure how well they are visible, but as the water was filling, one of these PMTs collapsed in, and this whole enclosure is filled or is under vacuum. So as this collapsed, the water rushed in from the tank and then created a shock wave that sent out, or that emitted out from this PMT, and then it caused other PMTs to also break. So it was a big chain reaction. So in total, about half the PMTs were destroyed, and here's a picture of what this looks like. So you can see that, the PMTs at the top here are still intact, but then everything below the water basically was destroyed. And so you can't see any PMTs below the water level because they've just all been shattered. So this was a huge loss for the experiment. But they were very persistent. So the director of Kamioka Observatory at the time, Yoji Totsuka, was quoted as saying, "We will rebuild the detector, there is no question." This detector was too important to neutrino physics to just kind of have this be the end of the experiment. So there was a big effort that happened to rebuild everything. So this is surveying the detector after the accident. People coming down on gondolas to look around and get an idea of what was everywhere. There was a new design for the PMTs. They installed this acrylic cover to all of them so that in the future, if there was another type of accident like this, the inflow of water would not create the shockwave. So there's this acrylic cover now to block that shockwave from happening. And then the key thing here was that in order to be ready for the K2K beam, there wasn't enough time to remake PMTs and wait for the experiment to turn on. So what they did instead was they took the PMTs that were still working and they put them in the positions where the other PMTs had been destroyed. So they redistributed them. And then finally, this is what it looks like when they're finally putting the last pieces in the detector. So this is what the experiment looked like after the PMTs had been redistributed. So you can see the density of the PMTs is much less, and there are still some holes, in fact. But this allowed Super K to continue running for the K2K experiment. So then the K2K experiment happened, and I just want to spend a little bit of time talking about how this works. So you can imagine a big detector like Super K. It's getting bombarded by cosmic rays, specifically cosmic muons, all the time. So I've plotted here the detector activity as a function of time, and each one of these bars is just a cosmic muon that's passing through your experiment. And this is happening kind of continuously, but from your team at the accelerator on the other side of Japan, they'll send you a signal that says, hey, expect a neutrino that's coming, and they'll give you a very small, narrow window to look for the neutrino. So these cosmic rays are coming a few times per second, but the neutrino from the beam is in a very, very tiny window, about 1/1,000,000th of a second. So there's essentially no chance that there's a cosmic ray at the same time as the beam neutrino. So everything that happens in this window, you can be pretty sure it's coming from the beam. And then, of course, the neutrino travels across Japan. It interacts in Super K, and it produces a charged particle. So this is what a muon looks like in Super K. This ring here is showing pattern of the hit PMTs that see light when the muon interacts. So they don't see the neutrino directly, they see the light produced by the muon traveling through the water in time with the beam signal from the accelerator. And so then here's what K2K measured. So this first plot here is showing the near detector data. The horizontal axis here is the muon momentum, and you can see the data compared to what the expectation was, agrees perfectly. So they were pretty confident that the flavors that they were seeing at the near detector were before any oscillations, before the neutrino had changed flavor. Then when you go to Super K, this is what they saw. So 250 kilometers later, they made the same kind of plot. So the horizontal axis here is the estimated neutrino energy. Vertical axis is the number of events. And then the gray dashed line is what the expectation was without oscillations. But you can see there's a big chunk taken out of it. And that chunk is well fit by something that looks like a sine wave. So essentially a neutrino oscillation. And what the dip of the oscillation tells you something about the amplitude, and then also the position of that dip tells you where the oscillation maximum is happening, and it tells you the frequency. But this wasn't enough data to really conclusively measure these oscillations, so of course we designed new experiments, bigger and better. But first I'm going to talk about what neutrino oscillations can also do, so confirming the tau neutrino. So this previous measurement by K2K was a muon neutrino disappearance experiment. They saw that the muon neutrinos disappear from what they expected. We can also do the other thing with neutrino beams. We can make a neutrino beam that produces studies the tau particles that are produced when the muon neutrino oscillates to the tau particle. So this is a picture of CERN, an aerial view of CERN. And CERN is famous for its Large Hadron Collider, which is shown here, so about 27 kilometers circumference. But kind of a little known fact about CERN is that they also ran a neutrino beam for a little bit. And that neutrino beam came off of this smaller ring within the LHC called the superproton synchrotron. And what this did was it accelerated protons just like at Fermilab into a target, produced a beam of neutrinos, and it sent those neutrinos from France all the way to central Italy, about 730 kilometers. And this ran for 6 years. And these neutrinos were a little bit higher energy because at the other end of this was an experiment called OPERA, which was designed to see tau neutrinos. And so I'll talk a little bit about how OPERA worked. So first of all, So opera is made up of little blocks, and each block contains plates of emulsion. And as the particles come through those blocks of emulsion, the particles leave tracks. And then after you've taken data for a couple months, you take out all the blocks and you scan them through a microscope that can then find the tracks in those blocks and match them all up and produce images of particle interactions. So this is an example of one of those. So each slice here, each vertical line is showing you one scan of emulsion. And then in the emulsion are embedded these little ticks that correspond to tracks. And then you can match all of these up and reconstruct the event. And what Opera was looking for was tau neutrinos appearing from the beam. So if you have muon neutrinos disappearing, like in the K2K experiment, you should see a corresponding increase of tau neutrinos appearing. You just need to have the right energy to produce them. So by zooming in really close on this event, what Opera saw was that there were actually these kinks in the track at the vertex of the event. So those kinks correspond to a particle decaying and changing momentum at a very short decay length. And so this is identified as a tau particle, actually. So what happens is the neutrino comes in, it produces a tau particle. The tau particle is so heavy that it decays very quickly. It doesn't travel very much. You can see the scale here is 376 micrometers, so it really doesn't travel very far at all. And when it decays into a muon plus a tau neutrino plus a muon neutrino. But you can't see those other neutrinos. All you see is the muon track. And so it looks like the tau comes in, decays, and then changes direction very quickly. So this was confirmation that actually when you have a neutrino beam with muon neutrinos, they do change into tau neutrinos. But you just needed a different detector to see it than the K2K experiment. So now we'll move on. Oh, actually, right. There's one other story about Opera, which I think Opera is, or maybe some people have heard about it before, but Opera reported that the neutrinos were faster than light from this neutrino beam. But at the same time, they encouraged caution. So in their paper, they write, the potentially great impact of the result motivates the continuation of our studies in order to investigate possible still unknown systematic effects that could explain the observed anomaly. So in other words, they measured faster than light neutrinos, but they weren't ready to claim that this was a revolution in physics, that things could actually go faster than light. But they were a little too late because they published, or they didn't publish, but they publicized their result. And then, of course, every media outlet on the planet picked it up. So yeah, there's a New York Times here. Tiny neutrinos may have broken cosmic speed limit. Roll over Einstein. I like that one a lot. Yeah, so there was a lot of buzz about this result, but ultimately what was found was that it was a loose cable that caused the timing offset. And it caused a delay of tens of nanoseconds that added up to produce a measurement that was faster than light for these neutrinos. So what's the lesson here? So I want to emphasize that science is a process that takes time, and these experiments are incredibly intricate. So it wasn't somebody from the outside world who looked at Opera's result and was able to conclude, oh, you've done something wrong. It was really engineers who were familiar with everything that was happening in the Opera detector that were able to identify this issue. It just took them a long time to find it. So what I want to emphasize is that when you see news articles like the ones I just showed, please check to see if the work that they're reporting on is published or peer-reviewed and not a preprint. So preprint is the code word for the experiment has put out the result, but it hasn't been peer-reviewed by other scientists in the community yet. So in this case of Opera, all the news articles were based on a preprint that Opera had put out and was waiting for community feedback on. So this is just one little tip. Okay, so moving on to modern day neutrino beams. So Opera and K2K were only 20 years ago, or Opera was 10 years ago or so, but we're still running neutrino beams today. So there are two features of neutrino beams that come into play. So the first one is going off axis. And what I want to talk about with going off axis is that, kind of the intuitive thing is to put your neutrino detector in the sight lines of your neutrino beam, so you get all the neutrinos. But it turns out that if you go off axis, something interesting happens. So you lose a lot of your neutrinos because you're no longer centered on your beam. You can think of the neutrino beam as kind of like a flashlight. So the brightest point is definitely in the center, but if you go off, you'll still see some. You're just not seeing most of them. But what's nice about going off axis is that all the neutrino energies start to get more similar as you go off axis, which means you can really dial in the exact energy of the neutrino that you want to see in your experiment. So I mentioned before that the oscillation proceeds as L over E. So if there's any uncertainty in your E, you're going to have kind of a smeared out measurement. But with this, you can really get all of your neutrinos basically at the same energy, so that when you do your measurement, you can kind of tune things so that you see the biggest oscillation effect with the lowest amount of background, lowest amount of other things that could look like oscillations. The other thing that can happen, or that you can do, is change the current on your magnetic horns that you use in your neutrino beam. So I showed this diagram before where the proton hits the block of material. The pions that are produced go through this magnet to be focused into a beam. If you turn the current around on that, you actually focus pions of the opposite charge. So now when these pions decay, they decay into antineutrinos instead of neutrinos. And so now you have an antineutrino beam. And modern day neutrino experiments use this technique to great effect. So in particular, there are two experiments I want to highlight. So the T2K experiment is an upgrade of the K2K experiment. So it still uses Old Faithful Super K, which was fully rebuilt with new PMTs filling in all the different spots by about 2006. But then it upgrades the accelerator at a slightly different baseline, and then it has a host of near detectors that are very advanced and use newer technology that allows them to really study the particle tracks in great detail. So here's just an example event from one of those near detectors. You can see instead of seeing a ring of light, you actually see the tracks of the particles. The problem is that it's hard to scale up a detector like this to the size of Super K. So it's still useful to have Super K with all of its mass at the other end of your experiment. It's just at the beginning of your, or close to the beam where you see a lot of neutrinos, you can make a detector that's very specialized and very exact. Okay. Then there's also the NOVA experiment. So this is the one I showed at the beginning. This is the beam that goes from Fermilab to Ash River, Minnesota. This is another view of the FAR detector here. The dimensions are 16 by 16 by 60 meters, so it's 14 kilotons. And there's also a near detector, which is designed on the exact same principle as the FAR detector, just scaled down, so a miniaturized version of it, like we saw with the K2K experiment. The way this experiment works is that each of these detectors is made up of blocks of scintillator that are in an alternating pattern. And as the particle passes through, or as the neutrino interacts, it produces these charged particles which create flashes of light in these scintillator columns. And then you can use those flashes of light to reconstruct the event, like I showed at the beginning, to figure out what happened. So these experiments have been taking data for a long time. Each one has been running for about over a decade, I would say. And they've been getting better and better. So this is a plot I took from NOVA from 2016. This is really showing the effect of going off axis and making a very precision neutrino experiment. You get a huge oscillation pattern, which you can see by the height of this bar here. So missing muons, looking for muons and seeing muons disappear is one way to talk about oscillations. The T2K experiment also saw electron neutrinos up here. So they did the experiment where they looked for electron-like events appearing in the FAR detector, even though they started with a beam of muon neutrinos. So this is a plot from that paper. And then, of course, the reverse horn current comes into play. T2K and NOVA have both repeated this measurement with neutrinos and antineutrinos, and they see a big oscillation pattern here. This plot is slightly different than the other ones. This is the ratio to the prediction without oscillations, so that's why it's flipped around. It's just the prediction without oscillations divided by, it's what they observed divided by the prediction without oscillations. But you can see really that almost all the muon neutrinos disappear if you get the energy just right at this particular point. Okay, I'm going to shift gears a little bit and talk about the other side of oscillation experiments with nuclear reactors. Okay, so nuclear reactors, the basic way that a nuclear reactor works is that there's some fission core that is creating energy through nuclear fission. That energy is turning water into steam, and that steam is turning a turbine, which is then powering a generator. And then the whole cycle repeats as the water is cooled down and recirculated. But the interesting part is what happens in the core. So in the core, you have a heavy nucleus and a neutron, and that neutron initiates fission in the core. So it splits that heavy nucleus into multiple parts, and it also produces more neutrons that can go on to sustain the nuclear reaction. Those lighter nuclei that are produced in the fission reaction are unstable, and so they undergo beta decay, like we saw in the first lecture. That beta decay produces anti-electron neutrinos and electrons. And so in essence, a nuclear reactor is kind of like a beam of anti-electron neutrinos. It's just not very focused. So to measure oscillations with reactors, what we're looking for is a anti-electron neutrino transitioning into either an anti-muon neutrino or an anti-tau neutrino. The only catch here is that the neutrinos produced by nuclear reactors are too low energy to actually produce the charged lepton associated with the other two neutrino types. So in other words, you can't produce a muon in the interaction because the initial neutrino has too low energy to do that. So all we can really do is look for these anti-electron neutrinos to disappear. But we've gotten very far with that. So I'll explain a little bit how this works. So with these anti-electron neutrinos, we use the inverse beta decay process to detect them. So this is the same technique that was used by Reines and Cohen for the first discovery of the neutrino. We've just gotten better at it over time. So, but the principle is the same. So the anti-electron neutrino comes in, it interacts in your detector with like a proton, and that produces a positron and a neutron. The positron produces a burst of light immediately, depending on what your detector looks like, but you see light or energy deposit from the positron. And then the neutron takes its time. It bounces around a little bit until eventually it too is captured and releases some energy that you can then detect. So it's really the combination of the prompt light from the positron plus delayed light from the neutron that allows us to say that a neutrino interacted in our detector. So I'm going to talk about the CamLand experiment a little bit. So this is CamLand, what it looks like. It is multiple layers of a detector that where the innermost layer is filled with liquid scintillator, which enhances the signal from the energy deposits in inverse beta decay. So the inner detector is filled with liquid scintillator. The outer detector is filled with water. That's just to block cosmic muons or to identify cosmic muons if they do enter your detector. You can see them pass through the outer layers of your detector first. There's also a radiation shield of mineral oil. And then the whole thing is surrounded by photomultiplier tubes to look at the light that comes out of these inverse beta decay reactions. So another picture of identifying antineutrinos in CamLand, same process as above. I'm just walking you through the steps. The anti-electron neutrino comes in, it interacts, produces this positron, which emits some light. Here's an event display of what that looks like in CamLand, and you might not really see any structure to this. But what I want to emphasize is that really the important thing about CamLand is not that there's structure, but that you can use the kind of weighted sum of all the hits in the all the hits in the detector to say something about the energy and the position of where the event happened. So in particular on this diagram, you can see that the hits are kind of clustered to the left side of this image. So with this data, you can then kind of figure out where the interaction took place. Now the next thing you want to do is look for that neutron that comes with the positron in an inverse beta decay reaction. So it will travel around and make another flash of light. So this is a picture of what that looks like. Again, you can see the hits are kind of clustered to one side of the image. And those two things combined give you a pair, a coincidence pair. And the idea is to count the number of coincidence pairs you have to say something about the anti-electron neutrinos that you've observed. So a little bit of history. CamLand stands for the Kamioka liquid scintillator antineutrino detector. We saw in the last lecture the Kamiokande and Super Kamiokande experiments. So CamLand is the next door neighbor. So when Super K was built, the Kamiokande experiment was decommissioned and CamLand moved in to where Kamiokande was. And so here's a photo of the installation of CamLand detector. What CamLand measured was the flux of all the reactors in Japan. So CamLand is positioned somewhere in the middle here, and then all these little red circles are showing you where the reactors were in 2002 when it made its first measurement. So what the model is basically you draw a circle around each reactor, and that's kind of the flux of neutrinos that you would expect in CamLand. So CamLand is seeing this constant flux of reactor antineutrinos. And what they measured was a deficit. So this plot is showing the distance to the reactor, and CAMLand sits at about, I think, 180 kilometers from all the reactors that it's measuring, or that it can see. And then all of these other kind of data points on the left side of this image are previous reactor experiments, which didn't see any deficit. They all kind of agreed with what the expectation was. So CAMLand saw reactor neutrinos disappear, but these previous experiments were too close to see anything. The oscillations hadn't turned on yet. The neutrino hadn't traveled far enough for oscillations to happen. But CAMLand is only one part of the picture, so having one data point is not really the most convincing thing to conclude anything about oscillations. So really, there was more work to be done to fill out this area here, and that fell to 3 experiments that I'm going to talk about just briefly. So this is a picture of the Chaux nuclear power plant in France. Another one in South Korea, the Hanbit nuclear power plant, and then finally in China, the Daya Bay nuclear power plant. And all of these power plants, 3 experimental groups installed detectors at each of these power plants around the same time. And they all kind of worked on the same principle as CAMLand. They had a detector that was capable of seeing anti-electron neutrinos, and they just filled in this oscillation curve of CAMLand at intermediate distances, so about 1 kilometer. So CAMLand was at 180 kilometers, and the previous ones were at less than a kilometer, so they filled in this region of around 1 kilometer. So 3 detectors, the double Chaux detector, the Daya Bay detector, and the Reno detector, each at their respective power plants. They all measured about the same thing, which was that they saw reactor neutrinos disappear at distances of about 1 kilometer. So this is the spectrum. The far Hall is shown in the black data points, and then the expectation without oscillations is shown in the gray. And if you take the ratio between them, you see this kind of dip in the data that shows that these neutrinos disappear. And you get a bit of an oscillation pattern. So this was in 2012. And then again, just like in all of our other experiments, we're measuring the position and depth of the oscillation to say something about the frequency and the amplitude of it. So let's take all of our pictures and kind of combine them. So these double Chaux, Daya Bay, and Reno experiments, they measure one oscillation at about a distance of 1 kilometer, and then CAMLand is measuring another oscillation at a distance of almost 200 kilometers. So the model here is really that there are 2 different oscillations happening. There's a kind of fast oscillation that causes the anti-electron neutrinos to disappear at short distances, and then CAMLand is seeing another oscillation that happens over longer distances. So the picture is that if you take these 2 results and you combine them, then you get a more complete picture of the oscillation. So it actually has a lot more structure than we thought. So the total oscillation pattern here is shown by this red curve. It's superimposing the frequency determined by double Chaux, Daya Bay, and Reno on top of the frequency that's determined by CAMLand. And you get this picture of oscillations that shows that there's a fast component and then a much slower component that takes a longer time to evolve. Maybe the last thing I'll say about this is that this is a log scale here, so that's why it's kind of distorted from the usual sine wave picture. But on a linear scale, it looks very much like a sine wave. So this is the full 3-flavor picture. And I just want to wrap up talking about the modern view. So we can kind of summarize everything we've learned into a diagram that looks like this. So what I'm showing here on the vertical axis is the squared mass of the different neutrinos that we know about. So I'm going to call these masses nu1, nu2, and nu3. And these are like the clocks that are ticking inside the neutrino that I talked about at the beginning. And neutrino flavor oscillations are described by different frequencies. And each mass state that goes into this picture is also a superposition of the flavor states. So flavor and mass are correlated, and mass and flavor are correlated, and we have that picture of how they mix together to describe the full pattern of oscillations. And what each experiment tells us is something different about this diagram. So from beam experiments, muon neutrinos change into tau neutrinos. We can measure that, and we can calculate or we can measure what the frequency of that is, and we find that there's a big oscillation for that. And so that's represented by the magnitude of these bars between for nu3, and then also this first delta m squared value here. That's a frequency. So the difference between the mass, this difference between the square of the mass of nu3 and the square of the mass of nu2. Camlan told us this value, that there's a longer oscillation. So a longer oscillation means the masses are closer together, and that oscillation happens, so I wrote a value here of 8 times 10 to the minus 5 eV squared, so it's about a factor of 30 times smaller than the one that's observed by the beam experiments. And then finally, these reactors at distances of about 1 kilometer, they measured the electron neutrino component of the same oscillation frequency that the beam neutrinos were measuring to build this picture of a full 3-flavor oscillation. Okay, so that's the picture, but there's still a lot we don't know about it. So the first one, the first problem with this is that the only thing that matters in an oscillation experiment is the difference between the frequencies. So if there are 3 masses, there are essentially 2 differences because the difference between nu2 and nu1 is very small. But more fundamental than that is that we can't really tell or can't ever say what the mass of the neutrino is, because all we can see is the difference. So it could very well be that nu1 is 0, but we don't know. We don't know if it's exactly 0, if it's heavier than 0. It could be anywhere. So we don't know what the baseline of this is. The other thing is that actually our picture gets more broken than this because I've ordered the neutrinos previously, but actually there are other orderings that are also possible. So in particular, this inverted ordering, where you make nu3 the lightest neutrino instead, is also totally allowed by the data. And again, this is just a feature of that we're only looking at differences. We can't see the absolute value of anything. In order to measure, or in order to tell apart the normal scenario from the inverted scenario, we would have to design an experiment that could see all 3 flavors participating in oscillations at once, not just looking from one flavor to another flavor, but simultaneously measuring the flavor change to all the flavors. So we still haven't done this yet. And then finally is we don't really know what the case is for antineutrinos. We can measure them a little bit with reactors, which tells us something, and we can measure them a little bit with neutrino beams by doing the reverse horn current, but there's still some uncertainty in what these values are in the antineutrino case. And it would be pretty interesting if we found that they would be different than the neutrino case, but we just don't have the precision to see that yet. So all of these and more in future lectures. I hope you come back to hear the rest of the stories. But I'll end it here today with just a summary. So we know that neutrinos are changing flavor, and their flavor oscillates because neutrinos have mass, and then reactors and neutrino beams are what provides us these measurements of neutrino mass. And then finally, with our new understanding from experiments on Earth, we're ready to look out into the cosmos. So next week, I'll be talking about neutrinos from outer space. Thank you.